Uh, I think it is working.
Yeah, it does. Okay, great. Okay, so unfortunately, we have to accommodate one virtual talk because Jana couldn't come in person last minute. A little bit about Jana. So Jana is the principal researcher in the algorithm Microsoft Research in Redmond, where he leads privacy-preserving deep learning projects at MSR. He also has an affiliate position with the Theory Group at University of Washington in Seattle. And in general, his research interests are in mathematical aspects of algorithm design, deep learning, and differential privacy. And today he's going to tell us about differentially private deep learning, unlocking the good tokens. So, Jana, you can start whenever you're ready.
Yeah, thank you so much. And thanks for inviting me. And I'm sorry that I couldn't be in person. Today, I'm going to talk about differentially private deep learning. So my background is in theoretical computer science, but I thought for this audience, I have never given talk at Crypto before. So I thought I will keep it as a conceptual level. So I will talk morely like how deep learning with differential privacy can really unlock some high quality data. So that's going to be the theme of the talk. Okay. And so in the last maybe like 6 to 7 years, there has been a kind of like a shift in the way the deep learning research is going on. And for the people who are work in this field, it is not a big surprise, but people who are perhaps are not like actively working in this field, there is a sudden sort of like a transition since the invention of transformer architecture. So there is like ML era before transformer architecture, and then there is this deep learning era after that. And the main change that happened with the introduction of transformer architectures, which are kind of like very abstract general purpose architectures, is that they tend to work very well for a vast kind of application. So you don't have to hand tune your own architectures and like come up with new learning algorithms and so on. So the transformers kind of like standardized the way the deep learning is being done, at least in the last 5-6 years. So just to give an example, I was reading the Llama 2 paper, which just came like a few weeks ago. And if you look at the architecture, the choice of the parameters, hyperparameters, and the algorithms they use, it's more or less unchanged from the BERT paper, or even like which appeared in 2018. So this is like 5-6 years is a very long time for none of these to change. So if you look at the kind of like deep learning that was happening before, there used to be like a change in architecture or something every 2 days, right? So that is a big shift in the way the deep learning is being done. And what that means for us privacy researchers is that the shift has focused, that has moved from sort of like this architecture algorithmic aspects of deep learning to actually the data. So in fact, it would not be an exaggeration if I say that like all the miracles you see in the last, using ChatGPT or like, the PAM models or the cloud models and so on, the primary, like the new thing that really happened is the data itself, the data engineering and the clever utilization of the data. Right. So that is kind of like a big deal. Like that is a big shift in the way the big deep learning has happened over the last few years since the invention of the transformers. But on the other side, like if you look at all these models, they're primarily trained on the data that is publicly available, which is not really high quality data. These are like Twitter feeds and like all the things that is publicly available. So in fact, like the case can be made that a lot of high quality data, which can really unlock the potential of deep learning, is actually private, like the healthcare data sets or education data sets. You want to build a good math tutor or like some other thing. So a lot of this data is actually private and it is not accessible to these large scale models. And the same is true in tech industries. I'm a researcher in the privacy preserving deep learning group at Microsoft Research, and we face that you cannot really make use of all the data unless you can ensure that there is a privacy preserving technology put in practice, right? So there is an opportunity here, and also there is sort of like an importance of privacy preserving technologies to really to really sort of like bring the value of the data to deep learning. And that's kind of like the premise of my talk. What I want to tell you is that the privacy preserving technologies, one of them I'm going to talk about today is differential privacy, but the principle itself applies to broader technologies, is that these provide a way to safely unlock high quality data. And hence, these will play a very fundamental role in advancement of AI. Right? Everything that can be done using the cheap data, we have made a lot of progress, but the big breakthroughs, for example, if you want to do more on medical data sets or like healthcare or like education data sets, there needs to be this unlocking the high quality data, and their privacy preserving technologies will play a very central role. That's sort of like what I want to talk about. So the way I'm going to structure this talk is like, I will talk about one technology or a tool which I research in, which is differential privacy, and how we can use differentially private, like do differentially private deep learning to protect against the misuse of the data or unintended misuse of the data. And I want to give some brief introduction to it for the people who are not familiar. And then I will tell about where this differentially private deep learning as a technology, like where we are at and what are the kind of impacts it already had so far. And then I will spend maybe like the last 25 minutes or 20 minutes to tell you about what it can unlock. Once this infrastructure of differentially private deep learning has been built, how we can use this infrastructure to truly unlock the data. And I will give you 2 examples of it. I don't think I will have enough time. So that's the plan. So let's begin. So what is the kind of problem you want to keep in mind? So I want you to think of the following. So there is a high quality private data set. You can think of it as a medical data set, or some, if you are in industry, this is some industry data set with like customers' data. And this is a very high quality data. You want to train a deep learning model, transformers, most of the times. And you want to make sure that the model you trained does not leak any information about the data itself, the training data itself. And here you could make various like assumptions about what do I mean by doesn't leak? Is it like the adversary has access to the entire, the data set, model weights, or he's just observing the API? I'm not going to be super careful about it, but because differential privacy is kind of like an information theoretic assumption, so we can even assume that the model weights are known to the adversary. Although in most of the deployment, it wouldn't be the case, but in general, we can assume that. Okay, and another small caveat perhaps is that when I say we want to train the model, we can start with something like GPT-2 or Llama models, which are already publicly trained on, say, Wikipedia dataset. So you don't have to imagine that every model we are going to start with a random initialization. Okay, so these are the 2 technical things, but this is kind of like the thing what we want to do. And I will tell what it means by training with differential privacy. It will give you some formal guarantees in terms of how much information is being leaked by this model. Okay, so I will define that, but this is kind of like the problem setup I want you to keep in mind. And now, what does it mean by training a model with training a deep learning model? So let's even recap what it means by training with SGD, which is one of the optimizers which is typically used. Again, I will not be super careful about the optimizer itself. Maybe there is SGD, people will train with Adam, but this is one of the learning algorithms. It's not going to play such an important role. So the magic of deep learning is fairly simple. So you have a pile of data, you randomly permute it, and you chop it into some batches. And then you compute gradients on these batches for a particular architecture. Again, here transformers using SGD as the algorithm. And then you calculate the average of these gradients, and you take this learning step where you update the parameters of the model. So this theta here is the parameters of the model, and you're going to take a descent step in that direction, right? So you keep updating this, and you keep repeating again and again. And one of the revolutions that has happened is that if you do it enough number of times on the vast amounts of public data and make the architectures long enough, then you see amazing behaviors we are now bombarded with in some sense. That's the magic of deep learning, right? It's very simple process. In hindsight, it's a very simple and elegant process. but it uncovers a lot of amazing phenomena. So this is training with SGD. There is no privacy at this point, right? So, but what, like, if you are a privacy researcher like me, you will be concerned that there is something like, something like nervous that's happening here, because in the sense that the algorithm, which is like the model weights, that is the algorithm itself, is now constructed out of the data. So the data becomes the algorithms, and you start to wonder, if I observe the algorithm's behavior, whether I can recover the data, right? I mean, this is a legitimate concern you could have. And in fact, that turns out to be true. Like, oftentimes, if you look at deep learning models and you look at their behavior, you can really reconstruct or a lot of the data, or at least you can make a membership attacks on them. So there have been many such works, which is showing that, in fact, this year PTS award went to this one of the data extraction papers from Carlini's group at Google. But this is one of the canonical examples. But there are several ways you can attack the models, deep learning models, and you can reconstruct it, or recover the sum of the portions of the training data. So this is not an academic thing. This can be done for very sophisticated models, including like diffusion models, GPT-2 models, GPT-3 models, and so on. So this is a legitimate problem. And as often happens in privacy and security, even one mistake can be can really be disastrous for the companies and organizations. So privacy and security have this one thing in common, in some sense, that even if on average your models are safe, one mistake is all it takes to really break the system, or cause deep losses to organizations. So that's what we want to protect against. And one of the technologies which mitigates this kind of information leakage through the models is the notion of differential privacy, which was invented at Microsoft Research by Cynthia Dwork and her colleagues back in 2006. And the idea is rather simple, and it makes sense from the perspective of machine learning. What it says at an intuitive level is that, imagine there are two data sets, and it only differ by one user, right? And here, unit of what I mean by one user, you can define, and that's what gives you the guarantees. But imagine this concerns the user's data, and they differ by one user's data. So then a model which generalizes, like a machine learning model, should not overfit onto this person's data. So that's, in some sense, what generalization actually means. So the way we can formalize is that if you train a deep learning model or machine learning models on these two data sets, X and X prime, they just differ in one person's data, and you observe the outcomes. For every outcome, the model which is trained on X, so this is the probability distribution. So there are no jumps in the probability distributions. If you look at the ratio of these probabilities, they're roughly comparable. So the e to the power of epsilon here, just really you can think of it as 1 plus epsilon, right? So the ratio of the probabilities is roughly the same. So the observer or an adversary who can see these distributions, he would not be able to distinguish between them. So that's what mathematically it means. Intuitively, it just says that you should not really memorize any data points. So that's what differential privacy guarantees, right? In particular, for the case of deep learning, and for the definition we will stick in the rest of this talk, is that here we will assume the model weights as the output. So what we want is an algorithm which guarantees that if I had removed certain users' data, the model weights, probabilistically speaking, roughly will be the same. So that's what we mean by a differentially private training of deep learning models. Okay, so this is a much stronger guarantee. I'm saying that even the model weights are robust to this, like adding or removing of one user's data. Okay, so this is what we mean by differentially private deep learning. And back in 2016, Abadi et al. Proposed a framework to actually train deep learning models with SGD. And their idea was actually pretty simple. So what they said is, okay, look, in the SGD process, which we saw earlier, where does the information regarding a particular user is being used? It's in computing these gradients. And that's where you actually touch the data. So how about we make sure that this step itself becomes private, right? And the way they propose to do it is to do the following, to do these two modifications to STD algorithms. So one is you now compute the gradients, but you clip the gradients. You limit the magnitude of the gradients. So the reason is that I don't want one person's data to really change the model weights too much, because that's my output. So you clip the gradient, that makes sense. And then you do the average of the gradient, similar to what you were doing before. And then you add a statistical noise, so typically a Gaussian noise, to make sure that the contribution of one user gets matched in this average, right? So this one step, like if you do it, you can guarantee, you can prove mathematically that it satisfies differential privacy, and you keep doing this again and again, like over all the epochs. So then you appeal to the so-called composition of differential privacy to really prove that the final model is private. Okay, so that was their suggestion. So it's a very nice and elegant idea, and they give, so basically you could think of like DPSGD as a new optimizer. It can actually replace SGD as the optimizer by these two small tweaks. And then you can guarantee that if I use this training process, if I use this optimizer, one, I can mathematically prove that it is a private, it will satisfy differential privacy definition we saw earlier, and it will, like, lead to a training of the model, right? So that's what they proposed. So at this point you might be thinking, okay, is the research done? Like, okay, differential private deep learning, does that simply means training with DPSGD as an optimizer, right? And right now, I have to tell you that there are plenty of libraries out there, like Opacus, TensorFlow, which support training with differential privacy, right? So, but that's not the whole story. So if you, okay, so they proposed an algorithm training with privacy, which is DPSGD. Indeed, you can train the models with them, but the problem is that when you want to train models for like practical use cases where you want to deploy and use them in real applications, there are many other factors that matter. Like, for example, you care about accuracy of the predictions. It doesn't just enough to say that my model is private, like how good is the quality of your predictions, right? I mean, otherwise it makes no sense. What about the privacy? Like, is the privacy guarantee strong enough, right? So there needs to be some care, because just training on this, like using the standard DPSGD algorithm, may not always give you the right privacy parameters for your applications, depending upon your applications. But the more importantly, at least from my perspective at where I work, the efficiency of the training process is equally important. For example, the speed of the training, the memory usage, the models trained with DPSGD, they have good inference latencies. Like, if the DPSGD algorithm takes 1,000 times more memory and it takes like 100 times more cost to train these models, then none of this even matters, because nobody's going to do with it, right? I mean, nobody's going to train models with that. And that all these things matters. Although we know how to train with DPSGD for deep learning, all of this should fall in place to really be useful as a technology, right? As a technology to be mature, right? And 5 years ago, the story was not that great, actually. I mean, I started working in this field about 5 years ago, and when I trained my first model, it was about 100 times lower, and the performance drop, even on some simple data sets, like let's say C410, which is kind of like assumed as solved in non-private world, the performance drop was about 30%. So that's really these kind of models you would not be able to deploy in any scenarios. You cannot develop applications based on that, right? So that was the state of the differentially private deep learning. But we have, as a community, has made a lot of progress in this field. For example, like as of today, the training with differential private deep learning is about 1.1x lower than non-private training. For all practical purposes, training cost the memory and the speed is not an issue. The performance drop is reasonable. There is a performance drop depending upon how much data you have, but that's reasonable within an accepted level, like maybe 1 or 2% drops. Privacy guarantees, we can still improve them. Like I will come to that point because I did not tell what exactly the epsilons we are going to use, but that can be improved. But we have made tremendous progress on that. But and also equally important that all of these things we can do now in almost like a plug and play way. Like there are many libraries and implementations readily available which people can use and train their models with. Okay, and I am from Microsoft and I work in this space, so I just wanted to say that a lot of these points I mentioned, our group contributed a lot, and most of the things I'm going to talk about is based on the papers we wrote in our group, which I have been one of the authors, and none of this is purely academic. In fact, Microsoft email server, the Outlook email server, now it's a language model for predicting sentence completions, helping you to compose emails and things like that. It's 100% DP trained. And so I'm not saying this to to make a point to Microsoft. I'm just trying to say that the technology is mature enough that even if industries can make use of them. So that's the point I was trying to make. Okay, so what I want to briefly talk about now is not so much about how we reach this point. Maybe I will mention a couple of cool algorithmic ideas that were necessary for doing this. But I want to spend more time on, like, given this infrastructure, what we can do after that, right? So there were quite a few ideas that we needed to reach this point. So for example, let's look at the 3 axes: privacy, accuracy, and the memory and speed. Sorry. So in the privacy, our group members, Gopi and other people, invented a new way of accounting for composing differentially private mechanisms based on numerical compositions, based on Fourier analysis and so on. And that really gave the tightest possible privacy analysis. So it was improved recently by a group at Google, but more or less, you can really squeeze out what is the exact privacy loss due to this STD process in the worst case. But yeah, and to improve the accuracy, so there were a lot of cool observations. So one of them is that when you start with pre-trained models, actually large pre-trained models, so something interesting happens to the gradients. So the gradients during when you start with the pre-trained model and then you fine-tune it on the private data sets, the gradients have this low rank structure, and the STD kind of like converges to a very good local optimum. So it's a very non-intuitive technical fact. I wouldn't want to get into the actual, we have some theoretical results on why this happens, and we can analyze it in some stylized ways. But really, we needed to understand a lot of the structure of the pre-trained models to really improve the accuracy. So that was one of the things we needed. And finally, to improve the computation and memory overheads, we had to tweak a little bit the STD algorithm. The tweak was small, but the kind of like the algorithms we needed was still quite a bit. And so we showed that in this paper called clipping, layer-wise clipping, which was published recently. So basically, intuitively speaking, what it says is that we need to, instead of thinking of PPHD as clipping the whole model weights, you kind of like isolate them per layer or per GPUs, depending upon whether you do distributed training, and you clip and add noise carefully to make it really efficient. So this is which is what got us 1.1 times slower speed up. So you need to be very careful in how you add noise, otherwise it wouldn't guarantee differential privacy guarantees. But yeah, but that's sort of like the details part of it, but high level intuition was that, okay? So to really achieve this point, there was a lot of work done. Our group has been played a significant role this end, but also outside, like from the academicians and also like at Google and so on. So And what I want to convey is that all of this work over the past 5 years really created this infrastructure for training with DPHD. Now it is really plug and play. There is, and you can actually train commercial systems out of it. Okay. So that's where we stand. Okay, so now if the infrastructure is ready, what are you going to do with that infrastructure, right? So that is the question I want to answer. So of course, it mitigates information leakage, right? This is by definition. Like if you train the models with differential privacy, it really helps you to make sure that the attacks on the membership attacks or data extraction attacks can be mitigated. It has been tested even on like empirically as well. It's not that the mathematical proof guarantees this. If you actually try to attack models trained on differential privacy, you can see that they are more robust to this kind of attack. So this is by definition is guaranteed, right? So the second, like the way the differential privacy unlocks is the value of the private data. So imagine the following, that you have a pre-trained model, something like Llama model or GPT-2 model, which is publicly available, right? But you have a medical application, or like maybe you have some, if you are in an industry, you have some customers' data, and you see that this data can really add a lot of value to this model, because these models have never seen, let's say, like images of cancerous nodes or something like that. How could you improve this model? By thinking of this as like, I start with this model and I train with DPHGD during this fine-tuning step, then you can really see that the model's performance improves significantly over, say, zero-shot performance, or and it comes with privacy guarantees for sure. So that you can see a substantial improvement in the performance of the public models. So this is really one key way where you can improve the model's performance. And again, like we have demonstrated this using like academic data sets and so on. Like there are several papers written by us where we showed that like even if you compare a privacy preserving deep learning using DPHGD versus a non-private algorithm, which guarantees you nothing, the performance drop is not too large. Maybe 3%, but these data sets are too small that there will be some drop in the performance, but it is acceptable. I will show you a little bit later how you can improve this. So there is this one maybe small aspect. This epsilon budget looks a little bit too large, like 6.7. I will come back to that later as well. But the punchline I want to say is that really these models are on par with like just training on non-private, right? And it's not just for like simple tasks like Glue. You can even do natural language generation tasks. I don't want to read this table, but really like even for generation tasks, like you can really fine tune them. So, and again, it's not limited to something like language models. If you're like worried about this, it's some similar observations how like the community has made. So these two papers from Google showed that you can also make these frameworks extends to vision tasks and really get non-private performances really using training with DPHGD, right? So it's not one of the phenomenon. And these papers also like opened up quite a few nice algorithmic challenges. Again, I don't want to get into too much details. For example, you can combine with this technology with so-called parameter efficiency, where you don't really need to update the model weights. You can only train a small fraction of them, or you can fine-tune the whole model. So all of these reach like similar performance. So this is great because oftentimes when you want to train with these models, you don't want to keep updating the model weights all the time. So this technology is like composes well with other advances people have made in like deep learning. So that's another finding these papers showed. But one, I mentioned a little bit about the performance drop and then the epsilon being a little bit too high for our taste. So that can also be mitigated if you really start using larger models, right? So larger pre-trained models actually achieve better performance and also the small drop in the epsilon. So I will show you what we can do with GPT-3 in a slide. And like if you are a privacy researcher and you have played with these ideas before, it's a little bit counterintuitive statements. Why is that? Like, you by using larger models where DPSTD is adding a lot more noise, actually leads to better performance. So this is because of some mathematical reason, and which I wouldn't try to get into. But roughly speaking, what happens is that when you do pre-training, the gradients during the fine-tuning step lie in a low-dimensional space. So somehow DPSTD can actually navigate this even without a careful reparameterization. Maybe this is a little bit vague, but this is the kind of like intuition. So this somehow DPSTD algorithm can navigate this low-dimensional space, and it requires a mathematical proof, which we had it in the recent paper in ICML. But yeah, so that there is a reason. It's not a coincidence that large models tend to give you better privacy and accuracy trade-off, because somehow they minimizes the intrinsic dimension when you're fine-tuning, and that couples with DPSTD pretty well. Okay, so and also I said that we can train larger models, but you can also do more complex tasks, like something like summarizations, where you take a long conversations and you summarize. So the data set I'm showing here, Samsung, is perhaps not the most sophisticated, but it is one of the academic benchmarks we use. But we have seen similar behavior even in industry level, the tasks. So summarization is considered one of the complex tasks, and you can also train the models with differential privacy, even including something like GPT-3, and you get very comparable performances with non-private models. And here, one point I want to make is that here, because you can use larger models, you can actually make the privacy budget also very small, something like 1 or even go below 1. And this kind of gets rid of one of the comments about using very high epsilon. So there is a trade-off you can make. But the main high level theme is that by using larger models, you can also improve performance, solve complex tasks, and get better privacy and utility guarantees. Okay, so this is the second point I wanted to make, that we created the DPSTD training infrastructure, and it really allows you to make use of this high quality private data in a privacy preserving way, as long as you accept differential privacy as a meaningful definition of privacy, and that is sufficient for your applications. Then you can actually train the models and get significant performance boost, and also make sure that it satisfies the privacy guarantee. So that is another way this technology can unlock the data, right? So now I want to shift the gears a little bit, which is this part of the story is what I found somewhat surprising to me personally. So I told you that the DPSTD gives you, when you train the larger models with differential privacy, the performance improves and the privacy guarantees are better. But in many applications, I cannot always use GPT-3. So let me give you one example. So you might have used GitHub Copilot or Codex models, which allows you to do code completions. They are not the biggest models. In my mind, that is one of the most sophisticated uses of deep learning technology or language models, but they are actually not that big. So the Codex model is about 1 billion parameters, which is GPT-3 on the other hand is 175 billion parameters. And there are reasons why people use smaller models, because the inference time and the cost of serving all matters in a real world applications. So just the prediction quality is not everything. The model has to also predict it quickly. So there is a lot of research that goes into making the model super efficient. By efficiency, both in terms of the cost of the model, but also just the inference time. You want to make the model super fast, especially for critical tasks. And we will mostly focus on task-specific models. We are not going to think about generic models, right? Not like GPT-4, which can do several things, but specific models maybe email completion models or your code completion models and so on. So how can you use privacy or differentially private training to really also compress the models? So there is like several interesting things that you can observe, but the most like really the main crucial observation is that when you take these pre-trained models like Llama models or GPT-2, they're trained on a lot of data, but the data is not very high quality, right? On the other hand, when you have a small fraction of private data, while fine-tuning on it, you can also make sure that you get rid of the model, which was not really the model weights, which were not really playing a role. So you can couple this fine-tuning with DPS3D to sort of like also compress the model, and you can do it in two ways. And I wouldn't get into. So one way is that you train while doing fine tuning, you drop some the model weight. So that is one way of doing it. And I don't want to get into the details. I want to show you something which we did this year, and that's called selective pre-training. So what I find it very interesting about this is that here you take a small amount of the private data and you use that not just to do the improve the performance, but also to compress the model, but really utilize this in all the stages of the model training. So typically people do the pre-training like Llama or like GPT-2, and then you do like fine-tuning, then they compress the model using some other algorithm and so on. But actually, if you had access to this high quality data, typically what is private data really brings to the focus, then you can filter based on this private distribution, some high quality tokens, and only pre-train on that a smaller model. And that actually gives you similar performance as a much larger model. Okay, so the standard pre-training is collect the data and train it to just max, so the maximize the next word prediction or like a minimize the cross entropy loss. But here we are saying that don't do that. So be careful in what pre-training data you do and pre-train only on that. So now you're making use of the data, not only just to improve the performance during fine-tuning, but also to really compress the model and improve the efficiency, right? So, and the way they do it, way we do it is as follows. I will give you a high-level framework. I don't want to give you all the details. So we have a private data and we have a distribution of that. So we collect all the public data, right? We still want to make use of the public data. So now we will train a classifier which kind of like learns this distributions of the private data and finds the tokens or the data point samples in the public data which has similar distribution as this. Okay. So and then once we learn this classifier, we train this classifier to classify all my public data points and rank them in some way, like whether it is more closer to my private distributions or not, right? So, and then you sort them based on that, and you only train on those samples with higher score, which is kind of like filtering these very good quality tokens for me, right? It is in some sense similar to what this concurrent work in the non-private world did by Michelle Chi and et al., the Persilian group at Stanford. So they proposed a different algorithm, but the idea is still the same, that like when you want to train the efficient models, you don't really want to train on everything. You want to be careful in the data you want to sample. So really our framework now, which is building upon this fine-tuning framework, is that you carefully select a part of the pre-training data and you train the small model. You wanted an efficient model and you train it on it. And then you do the fine-tuning, which we defined before, to improve the performance. Okay. So that sort of like is now we are using this private data not just to improve the performance, but also to sort of like compress the model, right? And again, this framework really gives amazing benefits, especially in terms of like inference optimal models, where you can not only just match the performance, in fact, like you can even improve the performance of a bigger model using a smaller model. And being like compress the model size by like 1/3 or 1/4, right? So this is very, very important, because the inference cost of serving these models is not that trivial. Like it's very high cost. So if you save it by like 1/4 of the size, that's like saving in millions. Like in Outlook, for example, like it gets so many queries per hour. So even small improvements is huge, but if you could compress the model by 1/4 of a size, so then really the inference cost. First of all, inference time improves a lot because the models are smaller, but in terms of even the pure cost, it improves a lot. Right. So this is another interesting observation that you can use private data, which is high quality, to also improve your inference time and reduce the model size. So now, if you're curious about it, you might be thinking, oh, because the assumption here is that the model size, and then, I mean, if you're familiar with neural scaling laws framework, so there is a trade-off between the number of tokens and the model size. This is what the field of neural scaling laws usually studies, right? But this scaling never takes into account what is the quality of the token. But in real life, not all the tokens are the same. So there is a trade-off. So if you have higher quality tokens, like if you can certify that this data set is much better quality, then you can actually train a smaller model to improve the performance. And here we used private data as a proxy for a good quality data. Because imagine a medical data set, it will be a high quality data set. I don't want to train on the internet to generalize to these kind of things. But you could say that, okay, so is the opposite contrapositive of this is also true. That is, like, if you don't care about the model size, then can you train on arbitrary data set? Then you can still reap some benefits. It seems to be also go in that direction, which is what we also showed here, that, like, for example, like if I trained with a Spanish BERT model or a Spanish GPT model, and I asked it to complete the sentences in English, it still does a very good job, but the model has to be significantly larger. Like, say, for example, here we use 739 million parameter GPT to match the performance of like something like 40 million parameter model. Like, the reason is that the quality of the data was not very high. So what I'm trying to say is that, like, so the privacy brings this data quality aspects to the scaling laws. So, and it really can change your scaling behavior if you are very careful about making use of this data in the entire pipeline. So one of the reasons people train bigger and bigger models is because they are not, I mean, like, the data quality is also in the picture, and it's not always very easy to like recognize what is high quality data. But for a task specific models, it's much easier job, and especially when we are assured, like something like medical data set or educational data sets where we know these are high quality data sets, we can use them to train smaller models. Right. So this is, to me, was a very surprising and very, like, in terms of like the commercial value of this, in terms of in applications in practice, this differential privacy as a tool for model efficiency is a very, very surprising applications. And it also sort of like tells you that the data quality plays a huge role. And that's one of the reasons why the privacy preserving technologies can unlock a very high quality data, right? So I believe I am maybe running out of time already. So I will conclude this by giving another example of synthetic data set, where you can also use privacy preserving technologies to create synthetic data sets, where you have a small amount of the private data. Let's say, again, like, I want to give examples of medical images or like educational data. You have few samples. But if there is a technology which can take these things in a privacy preserving way, of course, it can create a synthetic data set, which is of much larger size, then it can again unlock a lot of value. And we have made a lot of progress in this direction. And in fact, like, there was a very nice article in Nature very recently, 27th April this year, where they showed that if I had access to this good quality synthetic data sets, you can actually train models which may be even better than training on the real data. So this of course, this title is a bit sensationalizing this, but what they want to say is that a lot of the data sometimes is not very high quality, but synthetic data set, if you are good enough to design this data set using good algorithms, this could be even richer than some publicly available data sets. That's what they meant. And differential private, you can train like deep learning models, you can train like deep learning models with differential privacy to generate synthetic data sets. So it is one of the very compelling applications of DPSTD framework, which we talked about earlier. So I don't want to get into the details because maybe I'm already running out of the time, but even these kind of things, the technology is already reaching a stage where we can actually use them in practice. So we recently wrote a paper where we could even construct synthetic data sets even without training. I mean, one way to construct synthetic data sets is to construct via training with DPSTD as an algorithm. But even if you had only access to APIs of larger models, which have some public understanding of what an image is, you can take the private data set and you can interact with these large language models in a large models in a way that you can actually create a synthetic data set. Okay. I don't want to get into the details of it, so let me skip these 2 slides. But I do think that using differential private training as an infrastructure, we are at a stage where we can be able to produce high quality synthetic data sets. This is not a solved problem yet in my mind. I think there is a lot of work that can be done, but there have been we have already shown initial promise of this work. So there was one applications in Microsoft actually where we could really synthesize this customer reviews of the product. And when we trained the downstream model on that, it actually the performance was as good as it was trained on the real data. So synthetic data set is an exciting area, and DP provides a very good infrastructure for training that. Okay, so really the summary is that is one thing I wanted to convey in this talk is that training with DPSTD is the infrastructure is ready. It's almost plug and play. But now the focus shifts on how are you going to make use of the data? Because private data is usually very high quality. And also the data is at the center of deep learning now. So now the focus shifts on how we can make use of this. And I give 2 examples. One is one of the surprising things is that how you can use the private data to do the model compression and inference efficiency and so on. The other, which is equally exciting, is the synthetic data sets. And there is initial promise of this. And a lot of work can be done in this field as well. Okay, so I want to conclude with this. So I was listening to this very nice lecture by Ilya Sutskever, who is the co-author of AlexNet, AlphaGo, and GPT-3 papers, some of the seminal papers in deep learning. And someone asked him, are you worried about the data in the internet being running out of the data on the internet when you're training these deep learning models? And he thought for a bit, and then he said, it's not the number of tokens. The token is typically what the word for language models. And he said, what we really care about is not how many tokens, but really the good tokens. Right? That's what you need to advance this field going forward. And to my mind, the role of privacy preserving technology such as differential privacy is to really unlock these good quality tokens. So there is a lot of good quality tokens out there, like in education, in healthcare, but the privacy preserving technologies gives this infrastructure to unlock this data so that we can positively make use of these good tokens. And ultimately, DP research, to me, is a research about understanding the role of these good quality tokens. And I think there is a lot of exciting research questions you can think about in this. And I hope it was this talk gave you some glimpses of the kind of research you could do using DP infrastructure, training infrastructure, and having access to good quality data. That's what I wanted to say. Thank you so much.
Thank you. So we have a time for some quick questions. If you have a question, please come in front of the microphones. Go.
Hi, thanks for the great talk. At one point in the talk, you said that some epsilon choices were too high for a particular application. I'm wondering what sort of methods you use to assess whether a choice of epsilon is acceptable for a given application.
It's a fantastic question. So, okay, it depends on whether we want to academically speaking, you want epsilon to be less than 1. That's what I would say that argue is that is the most meaningful use of differential privacy, right? So and we could reach that stage using something like large models, and if you are careful in training and on academic data sets now we can get like comparable accuracies with epsilon less than 1, right? But let's come to real applications. For example, in Outlook, when we trained this model, we used epsilon equal to 4. So now, is it a good definition of, is it good value for training with differential privacy? The answer is not very like clear now. So so it depends on, like, what are the company's policies. Here in Microsoft, we were like allowed to use anything less than 4. But the way we really converge to some of the epsilon choices in many of the applications is really by attacking the models, like, at what time, like, the model behavior is robust. And also to note that, like, epsilon is a worst case definition. Even if, like, what we could see empirically is that even if epsilon equal to 4, in terms of, if you look at these distributions produced with the models and you try to do this hypothesis testing, the empirical epsilon you get is much better. That doesn't mean anything in mathematical sense, but it is at least saying that this assumption that, adversary knows all my model weights and all the data set except this one person's data set, maybe not the most realistic assumptions. So, but that's kind of like the long answer. So in industrial applications, yes, the choice of the epsilon is a little bit like a policy decision. But in here at Microsoft, we do a lot of, like, attacking of the models and try to empirically estimate it to see how good is this epsilon equal to 4. Is it really 4 or is it less than 4? And when we are satisfied that, okay, this is good enough, that's when then we chose this. But it's primarily, I mean, my background is in mathematics and an algorithm design. So in that perspective, it is primarily a policy decision, but it's not a. But yeah, but there is still backed by some empirical evidence that this is good enough.
Thanks.
Yeah, go ahead.
We have time for one more question.
Yeah, let's do one more.
Okay.
Yeah.
So, hi, Jana.
Hi.
About your statement about model efficiency and differential privacy, maybe I missed something, but I'm not sure if they're fundamentally related and helping each other. For example, if you look at your data selection algorithm, you could have easily used it for large models and it would be worked fine, it looks like. And you could have also, achieved model efficiency without privacy. So what is the reasoning behind them being more intimately, connected?
No, so you're right. So let me explain what I think of model efficiency. So maybe this example is what I was alluding to earlier, that imagine you have a medical data set or some healthcare data set, okay? So now there are two options for you. You either train with some privacy preserving technology, say differential privacy, or you don't want to make use of that, okay? I will just use a public model. It will be still fine. Say, for example, you want to build a doctor-patient summarization tool, GPT-3 can perfectly do this. But because it is not, like, it only has access to these bad tokens, or like the tokens which are not similar to the medical data set, it necessarily have to be large to really, like, fit well, to really summarize this. So the choice number one is that I will completely use a public model. It has no access to these private data sets. So then my claim is that the model size has to be necessarily large, and that's what we can empirically see. But now there is another choice to you, that I will use some privacy preserving technology, either differential privacy or some other definitions which you are comfortable with. So now you get access to this high quality data. So now you can use this, and we give one algorithm how to use it. And now you can use this to pre-train using much higher quality tokens. And it is well known. For example, there is this one nice paper called Beyond Neural Net Scaling Laws, where they say that if you could have trained these models on a higher quality tokens, you can actually don't have to train such big models. Okay. But in real world, like, it's much harder to differentiate what is a good high quality token versus not a high quality token. But when you know, the assumption here is that really the private data sets are high quality tokens. And now I can use this in my pre-training to really, like, get around this scaling behavior, where I can use fewer tokens and smaller model size to really match the performance of that, right? So I can give you an example that, like, Outlook email servers, the sentence completion servers, we could train a 40 million parameter model which matches exactly the same performance as GPT-2, which is about 1 billion model, 1 billion parameters, right? So in the end, it is a sentence completions model. So why is this disparity? Because GPT-2 was trained on all the public data sets, which is not really the most representative tokens you wanted to train. So in that sense, if you equate private data set as high quality data set, then the model, because there is this observation, which is we made it independently, but there is also some observations in deep learning that the scaling behavior of the models arises because we don't know what is good tokens and what is not good tokens. And if you don't want to differentiate them, then you need to train a much larger model. So somehow the larger models are more robust, even if the data is garbage. But the smaller models are not robust. So in that sense, that is where I'm connecting privacy with efficiency. It's basically the assumption is that private data is high quality data. High quality data means you can train a smaller model. So that is the connection.
Thank you, Jana.
Actually, we are running 10 minutes late. Unfortunately, we cannot answer questions. Thank you so much for the great talk.
Yeah, thank you so much.
In the next session, we'll have 2 more talks for contributed talks. You can hear me. Okay. In the next session, we have 2 contributed talks, and until we hit the break. The first one is the privacy-preserving tree-based inference with at TFHE, and our speaker is Benoit Chevalier-Mems.
Does it work? No? Okay, great. Hello, everyone. I'm very pleased to be here today to present you what we are doing in my team at Zama. I'm Benoit. I'm the head of a team who is working on a privacy-preserving machine learning framework. And today I'm going to present you the specific case of tree-based models. So how we turn them into their equivalent into FHE. I will assume that most of you know what fully homomorphic encryption is, so I will not cover the details, but just tell you that in FHE and notably in the crypto scheme that we are using at Zama, which is called TFHE, there are several operations, and the most important ones are the addition, the multiplication by integers, and the very specific operation as compared to other crypto scheme, which is the equivalent of table lookup over encrypted data. So that specific operation is really very important for us because it allows us to replace virtually any nonlinear function by its equivalent in over ciphertext. So that operation is what we call the programmable bootstrapping, so PBS for short. So very useful operation, but unfortunately a bit slow. So we will try to have as few of them as possible. So yes, the subject of today is how to turn tree-based models into FHE. So you may know that tree-based models are very important in machine learning, especially when it comes to production, because they are very efficient for a lot of things, including tabular data. So in tree-based model, we notably include decision trees, random forest, and XGBoost. And if you have a look to what a tree is, obviously you will see that there are conditions and that there are control flow operations, so branches, which are not very friendly, which are not naturally friendly with FHE. So at first sight, it may not look compilable into FHE, but we are going to show how you can replace some of the operations by things which are completely doable in FHE. So what we describe in the paper is a method that I'm going to describe here in the rest of the talk. Also an implementation. So we have implemented this and you can try it if you want. And we also have some experimental results. So we have tried the implementation over different data set to see how accurate it can be or how fast it can be. So let's go now to the method. So we have taken a lot of ideas from Hummingbird, which is an open source project by Microsoft. Hummingbird was originally made to support vectorization. So for another kind of use case, but in our case, it will be very useful because same thing, it will remove the use of branches. So the first idea is to replace the conditions, so the test of the conditions by a table lookup. So for example, if you want to check if ever x is larger than 2, you just compute t of x, where t is a table made by 3 0 at the beginning and then only once. And so you will see that the t of x is actually the Boolean coding for x larger than 2. So that's the first thing. And the second thing is that we are going to take our tree and after another round of PBS to compute a one-hot vector, just coding for which branch we have taken. So in the tree, the very small tree that I've taken as an example, you have 5 branches. So at the end of the second PBS layer, we are going to compute a one-hot vector of 5 bits. There will be 4 bits to 0, and the single 1 bit will correspond to which branch we are. So in the example I've taken, the branch 50 is the third branch. So it will correspond to a one-hot of 0, 0, 1, 0, 0. And then once you have your one-hot vector, you just need to multiply this vector with the expected values for the corresponding branches, and you will have your result. So let me explain how to compute the one-hot vector, which is the most complicated part. So the idea is the following. So let's, for example, take the 30 branch. So the 30 branch, you can see that it will happen if ever. So C1 is the top branch. Then on the left, you have C2, then C3 on the right, and the bottom, sorry, conditions. And the bottom condition is C4. So when do we have 30? So we have 30 when C1 is a false, and when C3 is a true. So what you are going to compute to have the bit of the one-hot vector corresponding to 30 is C3 minus C1. C3 minus C1 can have different values. The maximal value is 1 when C3 is 1 and C1 is 0. And except that, it's going to be smaller. So what you are going to do is to compute C3 minus C1, which is a linear operation, so it's very FHE friendly. And then you are going to have a PBS just to check if ever the value is 1 or if it is smaller. If it is 1, you will return 1 because that's a good branch. That's a good, final branch. And if it is smaller, you are going to return 0. So as you can see, it's possible to to compute all the bits of the one hot vector just with some linear operation and then a layer of PBS. So let's have a look to the full example. So on the left, you have an input, 12754. Then you have the first dense layer, just to map the inputs with the different conditions. So the conditions which correspond to C1 is first, and so on and so on. Then you apply the first round of PBS to compute the conditions. So at the end of the B computation, you have the encrypted bits for the different conditions. Then you multiply by C, which is the matrix, to compute the different paths in the tree. So you are going to have values that you compare in the D matrix with the maximal values. Only one of them will correspond. So here in our example, it's the 2, which is the second column, which corresponds to the max value in D. So you will have a 1 in the corresponding bit of the one hot vector. And the other values are smaller than the maximal value, which mean that the bit in the one hot vector will be a 0. So as you can see, D corresponds to which of the branches we have at the end. We have taken the second branch in the example on the top right. And you can see that at the end of the D computation, you have the second bit, which is activated, and the rest of the bits, which are 0. So all of this is still encrypted. And finally, you multiply by the value in E, which correspond to the different expected values in the few leaves. And you will have 40, which is the expected value at the output of the tree. So all in all, you have a few dense layers, which are very easy to do in FHE, and in particular in TFHE. And you will have 2 layers of PBS, one to compute the conditions and one to compute the one hot vector. This is the most complicated part of the talk. So if ever you have questions, we can come back to this later. So this was the method, and of course we have implemented this into the product. So if ever you want to try this, you just have to pip install ConcreteML, which is our product, and you can try it. So at the end, you will have APIs which are very close to scikit-learn, so they are equivalent in the clear. So normally, data scientists are going to be already familiar with the use of ConcreteML. And just at the end, when you want to do that in FHE, you compile the model, which means that you are going to replace the regular model by its FHE equivalent. And then you have new options in the predict, so to compute some predictions, either in a simulated FHE or with FHE computations for real. You can remark that there is an extra flag in the model, which is the number of bits that we use in the model, which corresponds to some quantization. So I'm not going to go too much into the details, but under the hood, there is quantization to integers. And depending on how many bits you use in the quantization, you are going to have models which are more and more accurate, which means that they are going to be closer and closer to the baseline, which correspond to computation in the clear. But at the same time, when you increase the number of bits in the quantization, the execution time is going to be slower because the PBS are going to be done over larger and larger integers. So we've made a few experiments, and most of the time we've seen that with 5 or 6 bits of quantization, you have results which are very close in terms of accuracy, and in terms of execution time, they are pretty decent. So depending on the use case, it might be few seconds up to less than a second. In the paper, you will see that there are more experiments with more execution time, more accuracies over different data sets. Also, if you want to see this in practice, we have a live demo on Hugging Face, which is about classifying some short messages, just to say if ever they are positive or negative. And obviously, the short messages are encrypted. So under the hood, it's done with some XGBoost. So you can have a look and see how it works. It's very easy. So to conclude, if ever this talk was interesting to you, you can have a look to all the details in the ePrint version. You can try the product just by downloading it and trying to reproduce the results, or you can also have a look to the implementation. Everything is on GitHub. And yes, we have a few examples on a Hugging Face. So the one I told you, but a few other ones if ever you are interested. And that's it for my talk. If ever you have questions.
Hi, very interesting talk. And I wonder, could you give us some hint about?
I'm not sure we hear you.
Oh, could you give us some hint about the performance of a PBS gate or how slow?
So one thing which is sorry, I don't see you. So one thing which is important is that in the TFHE version we use at Zama, we are not using the vanilla version of TFHE, which means that we are not using a Boolean only version, but a version of TFHE which allows you to manage short integers. So like 8 bits or a bit more. So that's one thing. And so your question was about, sorry?
My question was about the performance of a PBS, so how fast it is.
So I'm not able to tell you. So it really depends on the machine and the number of bits and also the norm. So let's say the size of the noise of the input. So it's not only there is no timing for an 8-bit PBS. It depends on what is this 8-bit. Is it an 8-bit with small noise or large noise? So what we are doing at Zama is that we have a compiler which is used under the hood just to manage this automatically. So it takes the noise at the beginning, it computes the noise in the circuit, and when there is a PBS, it knows what is the maximal noise. So what are the parameters to use at that moment.
Okay. Thank you.
Are there any more questions? Okay, let's thank Benoit. Okay, the next talk is private federated ensemble modeling for financial anomaly detection. And our speaker is Sergio Karpov.
Yes, so thank you. So I'll talk about the US-UK challenge we have participated in, and more details about the solution we have proposed 13th fair. So what is this challenge about? The United Nations estimates that 2 to 5% of global GDP is laundered each year, and this corresponds to illegal transactions, to money laundering, and different kind of criminal activity. So financial institutions and payment networks such as SWIFT, they have to combat, to prevent these illicit financial transactions, but at the same time, it must preserve, it must protect the personal informations corresponding to beneficiaries, for example, and of transactions and accounts. So the objectives of the US-UK challenge track 1 was to train a model to identify an anomalous transaction while preserving the confidentiality of very sensitive fields in the datasets. There were several organizers, institutional and industrial ones from US and UK, which can be here. So as a summary, we were given a task to train an anomaly detection system in a privacy-preserving manner, where we have several parts, several types of parties. The one part is the payment network, like SWIFT, for example, and the other type of parties is a federation of banks, which participate with respective account informations. So we have vertical and horizontal data stacking, transactions which are provided by the payment network, and the banks are providing account informations about this. This data set was highly unbalanced because it represents less than 0.1 anomalous transactions, which is very small. So on the size is like some kind of 3 million transactions and for 1 million accounts. And they were using the AUPRC scoring, which is highly adapted for imbalanced data because you don't want to have a high rate of false positives. So our solution is, as an overview, we have different parties, the payment network and the banks. And in the first step, we'll do an two-party MPCs where we'll do a PSI protocol between each bank and the payment network in order to detect the common accounts in the sets. And afterwards, having this intersection, we'll compute some features on the private data between both of the pairs, both. And afterwards, in step 3, we'll compute some local features from each of the party. And finally, we'll do an MPC step with K+1 parties, where we'll stack all this data and do a logistic regression. What about account matching and feature engineering? So as I said, we match the accounts from data and the payment network. We use this intersection in order to compute the joint features, like does transaction from the payment network and account match in the PI fields, private information fields. And we use secret hash comparison protocols here, which are simple and fast. And in parallel, each party, like banks and payment network, compute different private features which will help with a final model. Like the banks have some kind of account status log. Is the account closed? It is under monitoring, etc., which corresponds to an internal information of each bank, and it doesn't want to be revealed. And at the same time, we have the payment networks, which will do some kind of anomaly indicator features, like what is the frequency of sender hour pair, and how does this corresponds to the historical data? Is it an outlier or not, etc. Also, some kind of probabilities of a transaction being anomalous, like rule-based, network models, machine learning, etc. Once we have these features, we'll do final stacking. So the joint features, because they are two-party shares, they will be reshared to a K+1 party shares. And the private features will be secret share, simply secret share. It's easy to see how to transform two-party shares into K-party shares. The payment network will do the right reindexing, and each bank will do the reindexing of their shares. So we'll obtain a K+1 shares for free, almost. So here we are doing public reindexing, that is, we leak where the transaction is situated in the final data set for performance reasons. We can do it privately, but it will be more, the overhead will be larger. So afterwards, we train a logistic regression model in MPC on this stack data set. We have implemented it with the Manticore framework. We use PCA and internal normalization in order to obtain numerical stability, because all these steps we have fine-tuned the logistic regression. We do them because the data set is highly imbalanced and it is hard to optimize. We use second-order optimization for fast convergence. Only 2 iterations are enough. The sigmoid we compute it with high precision in order to be for result to be precise. So the resulting model, for example, the logistic regression coefficients are secret shared in the final, and they are kept like this in order to do the next step, which is the prediction phase, which is simply we repeat the first 3 steps, and the 4th step, instead of doing logistic regression training, we do a prediction with a secret shared model, and finally we obtain a transaction anomaly indicator, which is a probability either of lag, and we can reveal it to the corresponding standard and beneficiary banks. Nothing. So yeah, some details about what can be optimized here. So what about the implementation and the results? We have implemented it on Infer's XOR platform. It's about 100 lines of high-level code. It's a combination of MPC and plain text computations. And the logistic regression, the final logistic regression step is performed at a 3-party MPC for better performance. So here's, this is the code for logistic regression. It's quite simple. It is easy to implement it for PPC developers. So the organizers tested the solutions, the proposed solution in 3 different scenarios. The first one is payment network plus 2 banks. The second one is 4 banks or 9 banks. So finally, we have 3, 5, or 10 players in the protocol. So the execution time, it's in our file solution doesn't change a lot because of the fact that we use a 3-party computation at the end. So we don't have a quadratic explosion in the execution time. The communication, it's some kind of, I don't know, it's not big. And the score, it's 0.85, which is the same as if we have did the computation in plain text. And compared to a local model where only the payment network data is used, adding the data from the banks increases the model performance by 45%. So here on this slide, we can see that why it is important, why the federated learning is important in machine learning use cases, is because adding more data to the model, you increase its quality, even if you use simple machine learning models like logistic regression. So what are we doing in FAIR? In FAIR, we are a startup which we are doing private computing, mostly MPC, plain text, etc. And we are developing a platform where you can easily implement PPC algorithms with our technology. You can try it here. And I'm happy to take any questions.
Let's thank the speaker. If you have questions, please come forward. Okay, I'll start with the easy one. So I wonder, what is the trust assumption on the banks and on the servers when you do the logistic regression?
Trust assumption.
Is that like semi-honest or malicious?
No, it's honest. Majority, full threshold. And in our product, for performance region, we use a trusted yield for setup phase. We can replace it with interactive setup phase, but the performance will be worse.
I see, thank you.
Hi, thanks so much for the great talk. Maybe I missed this. You said that you were training a logistic regression model to identify, what is this to like flag accounts? Or I guess like, yeah, what are the features that are being pulled into, like, are they being trained over transaction data or other types of features?
It's, it was trained on you had the data set from the payment network. It has transactions where you have beneficiary and destination account, and also some information about the transaction. And for banks, you have a flag for the corresponding account if it's under surveillance or it is closed, etc. And also some, for example, the address of a beneficiary, etc. And when you here we have tried to do some feature engineering in Clear or in MPC in order to facilitate the logistic regression. And finally, in our logistic regression, we have I think we have 10 features in total with 3 million of rows. And the features are like, does the name match between the payment network and the bank data? What's the flag of this account? And some other features which were provided by the organizers. We didn't use we use the features for the baseline model, and we augmented it with features which are computed from both from the banks and the payment networks.
Thanks.
Welcome.
Okay, let's thank the speaker again. We'll have a 15-minute break, and we'll be back at 3:55.